Okay, so I'll be talking a little bit about low KV EDS and mapping. Low KV, we can do that on this microscope, that's not an issue. Mapping at low KV is going to be an issue with this microscope, as I'll explain a little bit about why low KV mapping and tungsten filament microscopes don't mix so well. But first off, we'll just talk a little bit about beam sample interaction and where the signals, the X-rays, actually come from, how acceleration voltage, beam current and probe size affect these things and how they interact, which is where we come into why tungsten filaments have some issues. And then we'll be looking at some different mapping examples. At the end of everything, I am going to pull up a few spectra live on the microscope showing some of the challenges you can face when you really try to drive to the very low acceleration voltages. But first off, the X-rays, where they actually come from and how it works. We have our electron beam coming down into the sample, and you will have to have an X-ray, you have to have the primary electron beam knock out a core shell electron. Then you have a drop down from the outer shell electrons. The energy difference in binding energy comes out as an X-ray. Those X-rays can come out in any direction. So we can see here, the red one is an attempt at illustrating an X-ray, and that's going into the sample, not out towards our detector. So we generate a lot of X-rays, and each of these subsequent electrons after the collision can generate new X-rays. So it's a cascade effect going down through the sample, and X-rays go out in all directions. Only a fraction of these will reach the detector. A lot of them will be stuck inside the chamber, inside the sample, end up on the chamber walls. Some of them will reach our detector, and then we can analyze them and figure out what's the energy and what element did that correspond to. So every time an electron is involved in a collision, it transfers some energy. And that means it loses energy as it moves down throughout the sample. So it can't excite high energy X-rays at all depth in the sample. They also lose their energy just simply by being slowed down in a continuum as they move down. And if you have a charged particle that's being slowed down or experiences an acceleration, it will emit energy or photons typically. And that's our background in the EDS spectrum, the Bremsstrahlung. So, since we lose energy from the top and going down into the sample, that means at different depths into the sample, we can excite different X-rays. But these X-rays that we generate down the sample, they are absorbed within the sample matrix. So one thing is how far down we can excite them. Another thing is what energy do the X-rays have to escape at certain depths. So just having an X-ray generated isn't enough. It also needs to leave the sample and get to our detector. So low energy X-rays, you don't need much energy in the electron to generate them. If we have 30 kV and we're looking at oxygen, which is at 0.5 to 3 kV, those we can generate quite deep down into the sample. So they have a large excitation volume. But the low energy also means that they are easily absorbed. So even though they have a large excitation volume, they can't escape from all the way down. So they have a large excitation volume, but a small escape volume. They don't have enough energy to go through several microns of sample thickness. For the high energy X-rays, our electrons, they have to have a lot of energy to excite the X-ray line to knock out the core shell electron. So since they need more energy, that means you can't excite the high energy lines as deep down into the sample as the low energy lines. You have a smaller excitation volume. However, the X-rays you do excite have a larger probability of escaping because they have higher energy. So their escape volume is larger. So you have these two effects that play into where your signal is coming from. And it all depends on your sample mix and the different X-rays that are involved that you're looking at. So depending on if I have a heavy element sample, my light energy X-rays will have a very shallow escape region. Whereas if I have a light element sample, I'll have a very large escape region. If we try to run a simulation of it, this is a silicon sample. I'm using the Casino software. It's free. Google it. I'm told, depending on where you're at, don't Google Casino from your work computer. But if you do electron trajectory simulation, you should find something suitable. So this is a silicon sample modeled at 30 kV. Blue that's the electrons coming down. The red, that's the backscatter electrons escaping the sample. And just for reference, it could be a little hard to see, that bar down the bottom is about 7.3 microns into the sample. So you can see we penetrate, the lowest energy electrons die out about 8 microns into the sample roughly. If we do the same thing at 5 kV, the images look sort of similar, but the scale bar is very different. So at 5 kV, my electrons are only penetrating about 300 nanometers into the sample versus several microns at 30 kV. So my electrons are much more confined to the surface. That's one thing where our electrons end up, but what's more interesting from the point of view of X-rays is where does the energy end up? So these curves are where the energy distribution goes out, and the outer one is, as far as I can see from here, at 5%. So the outer one is where the electrons have about 1.5 kV of energy left. Everything else been deposited within those lines. And again here we have about 6 microns. If we look at 5 kV, shape slightly different. You get different transmission down. But this line is about 200 nanometers. So again, your energy is deposited much closer to the surface. This is in a gold sample. Same thing, 30 kV. Let's go back. So for the silicon, 6 microns. For gold, 30 kV, 600 nanometers. So silicon at 5 kV, the penetration depth of the electrons similar to gold at 30 kV. Of course, gold is a very heavy element, but it illustrates that depending on your sample configuration, you'll have very different escape and interaction volumes. 5 kV for gold, we're at 50 nanometers. So at 5 kV in gold, we're starting to get very surface sensitive. If we look at real spectra, this is a Teflon sample. So these are all light elements, same matrix, and I acquired them at 5 kV, 10 kV, and 20 kV. They're rescaled to the fluorine peak. And we can see as we go up in energy, we lose relative intensity on the carbon peak. Because in this case, fluorine is the heavier one relative to carbon. If we run the simulations, you'll get something like this. You can see the red line is fluorine, and you generate, this is the detected X-rays. You can detect X-rays that were generated as far down as 4 microns roughly in Teflon at 20 kV. Whereas the carbon, we're starting to trail off around 2 microns. As I reduce my acceleration voltage, these curves move slower. The scale down here creeps in. This is 1.5 microns, so we're getting more surface sensitive. And the fluorine and carbon signals start to come from the same region. And here at 5 kV, we're probing the same region with both carbon and fluorine. And that's what we see in the relative intensity change on the left-hand side. One thing to note here is that we're getting more and more surface sensitive. End of the scale was 5 microns here, almost 2 microns, 500 nanometers. If you look at these spectra, we can see, I've been talking about the fluorine and carbon peak. The red one is the 5 kV one, and we can see we now have a slight oxygen bump. Because we're getting more surface sensitive, we start to see that's actually oxygen on the surface. It's not in the matrix because it's drowned out when we have a large probe depth, but there's a slight surface oxidation or some oxygen bound in other ways on this Teflon sample. So that's one of the reasons why you would want to go to low KV.
Is that generated in the casino software?
Yes, this is also simulated in the casino software. So low KV means high surface sensitivity, and that's one of the primary reasons we want to go to lower energy ranges. Other can be your sample. If you have a beam sensitive sample or you don't want to deposit charge too deeply into it, it's another good reason to go to the low KV range. But that gives us few issues. So basically the acceleration voltage or the electron energy is defining for how far down can we generate X-rays. We need low acceleration voltage to be surface sensitive. But the probe size, the spot we have on our sample also have a large effect on where we are getting our information from. The depth we're getting information from is limited by the acceleration voltage. The spatial in the 2D resolution, what we normally think of as resolution when we look at an SEM image, in the EDS images, X-ray maps are also limited by the probe size, not the acceleration voltage. So if I have a large probe, my images are going to be smeared just as they are in the SEM. So, good resolution, both EDS and SEM, we need a small probe size. To have a small probe size, what you do normally in an SEM is go to a small aperture, low beam current, high acceleration voltage. Which means if we do this, we'll have very few X-ray counts and we'll be getting them far down into the sample. So signal to noise ratio, fast data collection on the EDS, we want a large beam current. These don't play well together. We want a low beam current to have good spot size, and we want a large beam current to have good data collection, good statistics. In the tungsten and lab 6, like we have here, the source size is large, so they inherently have a larger spot size than the field emissions. That is what it is. The problem is they also have a larger energy spread than the field emissions. And this comes into play when we decrease our acceleration voltage to become more surface sensitive. The energy spread results in more chromatic aberration as we reduce our acceleration voltage, which means on a tungsten emission microscope, you can't have typically a small acceleration voltage and a small probe at the same time. Your probe goes increasingly larger as you decrease your acceleration voltage. You don't have the same problem on a field emission. So, same thing if we increase the beam current by putting in a larger aperture, we get a larger spot size on the sample. So again, not what we want for high resolution. We have a few different settings. On the field emissions, you can usually change your condenser lens. That works the same way as opening up your aperture. Again, you get a larger probe size, so you lose your resolution on the, in the maps. And one thing to be aware of, spot size, it's a common name in the different microscope manufacturers. It has nothing to do with your physical spot size. It's an arbitrary number. Spot size of 1 doesn't tell anybody anything about how large the spot actually is. Spot size of 1 is going to be very different at 1 kV versus 20 kV. So spot size is just an arbitrary number. 1 is smaller than 2. That's all you can learn from it. So a couple of examples how it all affects. This is a silicon substrate. If you take a lighter and flick it, so you get sparks from the flint. The flint is actually a bunch of rare earths, lanthanum and cerium. And they generate these nice round particles as they cool down, as they're flying off. So it's a good way to create particle samples, and you get some very small structures as well. These larger spheres are micron sized. The one we have up here, I extracted a line profile from the SEM image and looked at roughly full width half maximum of the increase when scanning over the line. We have about 400 nanometers on this particle. If we go down to these small structures we can see in the lower left, just outside the larger particle, we have about 90 nanometer line width across those. And those are again very small round particles, most of them. If I acquire an EDS map of this, The typical recommendation and typical rule for it is you get micron-sized information in an X-ray map. Well, not quite. This is the secondary image. This is our counts per second image. The counts per second is all X-rays, just where are the X-rays coming from. There's a couple of things to note here, that the detector in this acquisition is mounted up there. You can see shadowing from the large particles because X-rays can't escape from behind that region. But we can still make out some of these smaller features. They're not clear in this image, but they're there. If we go in and look at the individual maps, this is silicon. This is the substrate. So we can quite easily see the black spots where the particles are. We can also see some of the darker areas where you have shadowing of silicon by the nanometer structures that are on top. And if we look at the cerium map, it's a little hard for you to see down there, but these structures down here, you can actually see they are round particles. The 70 nanometer line I extracted from my SEM image are made up of even smaller cerium particles. So right here we are imaging, in X-ray imaging, 70 nanometer or smaller particles. You can easily get good high resolution EDS maps. This is at 10 kV. I'm just going to run through some of the other elements we have in there. That's lanthanum. So the larger particles are primarily cerium and lanthanum, the rare earths. We have some iron in there. You can see a lot of the smaller particles are iron rich compared to the larger ones. And again, we have very nice resolution on the small ones here. We have carbon all over the place, confined on the particles primarily. And the particles, all of them are oxidized, as I would expect, because high temperature and they've been flying out in atmospheric air. So everything is oxidized except the substrate, which is pure silicon. Cerium, we have a couple of different options for when we're mapping that. This is the L-line map. We also have the M-line map. This doesn't look very nice compared to the other one. And that is because if we look at the spectrum, I'll just go lanthanum, we have the same story, lanthanum L, lanthanum M. You have a lot more noise in the M-line map. If you look at the spectrum, up here we have lanthanum and cerium. They're nicely separated and we have quite intense peaks. And if you look at the background tail, that goes down. So the peak to background ratio is quite good. If we go down in the other end, we have going down up from the bottom, we have the carbon peak, oxygen, iron L. Then we have lanthanum and cerium nicely overlapped down there. So even though that looks like an intense peak, start by looking at the background. So subtract the background. Now the peak is suddenly not so intense anymore. And then divide that peak into two different elements, because that's a combination of lanthanum and cerium. Then you don't have very many counts down there. So that's why the maps are more noisy. And this is a challenge of going to low energy. You get less counts, you get more background. And at this point, every single count you can get to build up statistics really start to matter. So again, this is what we got at 10 kV. And if I increase my beam current, so here I have 0.45 nanoamps. Increasing my beam current means I get a larger spot. And you can see everything is smeared out. Same actuation voltage. This is purely an effect of the beam probe size. We can see it in the secondary electron image. So on the left, that's our SEM image. On the right is the total CPS for X-rays. If we go in and compare the individual maps, here we have our oxygen and cerium. Everything is smeared out. Same actuation voltage, so we're getting information from the same volume. But what we're seeing is our resolution is limited by the probe size here. If we go the other way, that's the original one. This is at 30 kV. We still have nice resolution in the secondary electron image, but our CPS map, all of a sudden, it's much more uniform. We're no longer seeing the strong shadowing, and we're starting to see, if I go into the maps, silicon, cerium, silicon and cerium. At 30 kV, I get silicon signal going through even my heavy cerium spheres on there, because I am generating a lot of X-rays and some of them can escape through. I'm changing my probe depth and my interaction volumes. Again, 10 kV and half a nanoamp, 5 kV and 0.4 nanoamps. So I lose a little bit going down in 5 to 5 kV. My probe size increases a little bit, but my interaction volume is now significantly closer to the surface. Just show that again. That's the 10 kV, 5 kV. If I go in and look at the elemental maps, 10 kV for silicon. Note the shading of the particles, the smaller particles we have on there. And as I go to 5 kV, that's going to be much more obvious because I'm closer to the surface. I'm not, even though these are nanometer-sized structures, they're still attenuating the X-rays coming down to my substrate. So I have, electrons coming down to the substrate. My electrons have less energy as they come down, can generate fewer X-rays, and the X-rays still have to escape through the thin layer that's on top. So 5 kV, I'm much more surface sensitive. But now I'm limited to my cerium M line. I no longer have the L line available because cerium M is up above 5 kV. I can't excite that line. So it starts to get a little crowded down there when you go to low energy. All your lines are squeezed into a narrow region. Certain elements you can't even detect anymore because their lines will be too heavily overlapped. These are the other maps, the iron L line map now, not the K line. I was using a 10 kV, but L line. So again, down in the very low energy range, we have the oxygen map. And if we correlate the oxygen and the silicon map now, you can see there's a very good overlap between them. See, all the oxidized particles match up to the black parts in the silicon. I'm getting very surface sensitive now, even on the oxygen signal, which is usually a light element, and we say that's usually coming from all over the place because you can generate them very far down into the sample. Going down in acceleration voltage, you limit where the X-rays are coming from. Quick look at acetaminophen. This is carbon, hydrogen, nitrogen, oxygen. I use this as an example of how low can you actually go and still get a signal. Well, these are acquired. The red one is at 3 kV. And I reduced the acceleration voltage. They are scaled to have same height on the carbon peak. And as we go down, we have 3 kV, 1.5 kV, 1 kV, 800 volts, 700 volts, 600 volts. So even at 600 volts, I'm still getting a signal from my acetaminophen that I can use for something. But look at the oxygen peak. As I said before, we had this change in ratio depending on our excitation volumes and escape volumes. The problem with the oxygen peak is that 600 volts, that's not a lot of overvoltage compared to the oxygen absorption line. We're running into the problem where we can't excite the X-ray lines anymore. And that's why we have a relative decrease of the oxygen peak. It's not just our change in excitation volume. It's also that we are exciting them less efficiently. Of course, the marketing approach to this is not look at the decrease in my oxygen signal. Let's rescale it to the oxygen peak and say, let's look at the amazing increase in carbon signal instead. Depends on what you want to look at. But when you move into the low energy range, you start to get very limited in your line selections and what you can actually do. And for this, I would like to show a couple of spectra from this system. On here we have two different detectors. One is on this side is our regular detector with a polymer window, and on the right-hand side, the black one, that's with a silicon nitride window. So there's a difference in the window technology here. I used our team software for all data collection and most of the data analysis as well. So if I just go in here and collect a spectrum, right now I have my microscope at 2.5 kV. And I will just change the scale to go all the way out. This one out here is silicon. Then we have oxygen, carbon, and down here we have silicon L line. I'll just try to redo this with both detectors enabled. And let me just do the overlay of them. The red one is the silicon nitride window. The line that's overlaid is the polymer window, and they're rescaled to the silicon peak on your right. And you can see silicon L. We're so far down that in a polymer you get heavy absorption. The nitride window is a lot thinner, so that means more X-rays can go through. So you have a strong L line here with the nitride window that you wouldn't have with a polymer window. So if we try to dump the voltage a little further down to, let's say, 2 kV instead of 2.5, do the same acquisition. The silicon line is at 1.74, but we are at 2 kV, which means we don't really have enough overvoltage to excite the silicon line. It is there, very small peak, but with the nitride window I still have a nice L line peak I can now use. And if I go down even further, here we have 1.5 kV, and do the same thing. I can still get a silicon signal with the nitride window. Of course, you're limited by what element lines do you have within the energy window you're probing. And as you might also have noticed, right now I'm only getting about 400 counts per second. Before I had several thousand. Because we're reducing the energy of the electrons coming down, we're reducing the number of X-rays each electron can generate, which has a severe effect on our count rates. So down here, every single count you can get matters. You want to get your detector close in to actually capture everything. And if you're trying to look at lines that are lower, then moving down to L lines becomes something that's possible. Though I will say, when we're down here, try to look up the theory for the position of the L lines and figure out what the background correction should be at L lines. This is somewhat unexplored territory. Silicon L lines, the exact position will depend on the binding configuration. We're so far down that we're starting to have valence electrons involved in these transitions. And the valence electron energy depends on the binding configuration. So silicon L line for pure silicon will be at one position. Silicon L line for silicon dioxide will be slightly shifted. So it's not exactly clear anymore what's the position of the lines. Another thing to take into account, we are now generating X-rays very, very close to the surface. We're really talking about nanometer depth here. If I have a dirty sample with carbon on top, I'm not going to see silicon, I'm only going to see carbon. As we move down into low energy spectra and mapping, cleanliness becomes very, very important. Another point why I wouldn't want to use, well, it works for now, but I wouldn't want to leave the beam burning at the same spot for half an hour and try to do this again in this microscope. If your vacuum is dirty, you're going to build carbon on top, you'll lose your signal after a while because you simply have more attenuation. You're building up a carbon film in there. I've been waiting a while to get my hands on one of these detectors for real on my own microscope at home, so I can start looking a little more on the L lines, because with the polymer windows, you have no chance of mapping silicon in this range. So, point of it all is, you can easily image structures that are smaller than the interaction volume. At 10 kV, the maps I showed, I'm still probing quite far down into my sample. We can see I have silicon signal escaping from beneath my structures. That doesn't mean I can't image them. I could still see my 17 nanometer particles spread out on the surface. So X-ray mapping doesn't necessarily mean low resolution or small, that you can't see small features. Depth resolution, if you want to be surface sensitive, the only way to go is really to reduce your acceleration voltage. Point-to-point resolution doesn't really matter much what the acceleration voltage is. It's heavily defined by your probe size though. As you reduce your acceleration voltage, you typically end up with a larger probe. And if you listen to the recommendations we give for count rates, you lower your acceleration voltage, all of a sudden you lose all your counts. The normal thing to do is crank up your beam current to get those counts back. But that will increase your probe size, so you lost the benefit in spatial resolution of going lower. You do not need low acceleration voltage to image the small features. I could do that at 10 kV, 15 kV, 20 kV as well. I do need low acceleration voltage if I want to look at only the surface. If I want to get rid of that bleeding through of the silicon substrate, that's where the acceleration voltage comes into play. Surface sensitivity, low acceleration voltage. If you're looking at thin films on top of a substrate, you typically do want to reduce your acceleration voltage so you get signal only from your thin film, not from the substrate. And you do need a small probe size. Not necessarily small acceleration voltage, but small probe size to get good spatial resolution in the X-ray maps. So, quant maps, I only showed you the spectra. I didn't hit our quant button for a very good reason. To do quant on these things, you need very high statistics. And especially when you move into the low energy range, it becomes an issue to get enough statistics to do good quant, to really have an idea of what the models you should apply in there are. So even if I can acquire a map where I can see my features nicely distributed for maybe 1 hour, depending on microscope settings and everything, if I wanted to do quantification on it, we're not looking at 1 hour anymore. We're looking at maybe 10 hours. That's not saying you can't do it, but statistics really matter if you're trying to do quantitative analysis. And that's probably something we'll be bringing up in another talk. So, point is, low acceleration voltage, it's not too hard if you have a field emission. Small features, you can easily see them in X-ray maps, but you do need to play around with your settings depending on what you want to see.